roll with it.
And you know, to everyone who is there today, thanks a lot, I mean, for coming. I know it's kind of end of the day on Monday. Well, depending on where you are, not on the West Coast yet, end of the day. But also, like, this is Fusion Energy Week, and most of us here are some way related to fusion or interested in fusion or have thought about this. But I have tried to also ask a lot of our, high school teachers and students to come in. And if it is not finals week for them, they might. And so it will. We want to keep everything on a very high level, so everybody can understand. So it's not. We will like not to be very technical about the details, and in that garb, this is, it's a panel discussion. Sometimes feels like it's something very formal and stuff, but I hope it is not. This is more like the structure of a panel discussion, but the organic, attitude of a fireside chit chat with with coffee. Well, there's coffee inside it. And so in that, I guess it's been a couple of minutes. Then maybe we can just start with introductions. And but even before going to the introductions, I want to share something which is very dear to me. That fusion is one of the holy grails of energy production. We know that, all of us know that. Hence, we are interested in that. And a lot of scientific development has happened in the last many decades. But one thing we should always remember, that behind the science, it's always human beings, people, students, and mentors who do the actual work. And I'm so very happy that when we were looking for who wants to participate, and thanks to Noah and Eva and Yashika, Jessica, Sydney, everybody, is that there was this naturally, organically, it happened that we have students who wants to participate, and we have students at multiple levels. So let us go over, we know who the panelists are, so we can passing the, like as if passing the parcel. I'll call out a name, introduce yourself, and then that person can call out the other person until the whole panelists list is over. Then we can start the formal, chit chat about fusion. And so I'll probably start with our youngest member. I'm being old. Sydney, you want to say a few words about yourself? No?
Hi, for anyone that doesn't know me, I'm Sydney Battles. I work with Dr. Costa Nova, and I'll go over it in a little bit, obviously, but I work with the energetic electrons and space plasmas. So we're an interdisciplinary group, so I got the interdisciplinary work of working with fusion plasma as well as space plasma.
Cool. You can call out somebody, or I can. Okay, then I'll call out Jessica, because our other student.
Hi, I'm Jess Eskew. I'm a fourth year PhD student, also working with Eva Kostanova, and I am looking at the fusion side of energetic electrons. And to do that, I look at data from D3D, and that's where I'm currently at right now through the DOE SCGSR program. And how about Eva can now?
Yes.
Hi, everybody. I'm Eva Kostadinova, and I'm a professor in the physics department at Auburn University. And as you heard, we do interdisciplinary plasma, which is a lot of fun because it helps us connect the different communities. And basically, the connection is that science is kind of universal when you talk about fundamental problems, such as those energetic electrons that you're going to hear about. And next, I will call Yashika.
Hello, everyone. I'm Yashika Ghai from Oak Ridge National Laboratory, and I'm a theory and computation plasma physicist in the Fusion Energy Division. And today I'll speak about some of the fusion wave particle dynamics that also occur in space plasmas. And next, I'll call on Garima Joshi.
Hi, my name is Garima Joshi, and I'm a postdoc at UCLA. I'm an experimentalist. I study arch plasma in the laboratory, and I call on Noah.
Hello, I'm Noah Hurst. I'm a scientist at UW-Madison. I work on the Madison Symmetric Torus experiment, studying a variety of different things. But today I'm going to talk about self-organization.
Who do you pass on to, Noah? No. Uh,
Who else do we have?
Okay, so it's me and Elon. So
Okay.
let me talk a little bit about Elon. Elon is our fourth year graduate student. We call her late stage graduate student. Elon is driving back from her grandma's place in Jacksonville to Auburn, and she's on the way. She'll be here with us in 15 minutes or so. Traffic. But so we'll introduce Elon formally when she gives her spiel on filaments at the edge of like filaments in high magnetic fields. And I'm Saikat. I am a research faculty at Auburn University. And in addition to physics, I mean, I just like doing research in plasma physics. I love mentoring and working with the students, and also like soccer and hiking and okay, all sorts of things. So with this, well, today is also, if you don't realize it, 4th of May. So those who are Star Wars fans, may the 4th be with you. And we might end up saying that may the fourth state of matter be also with you, which is plasma. So I would like to go, I know there's a lot of students also in this, in addition to all our scientific researchers. So let me go through a little bit of what we are talking about, make a platform on which everybody else can connect to. So we probably already know that we're talking about thermonuclear fusion, and in thermonuclear fusion, what we have is the deuterium and the tritium. They fuse to produce helium and a neutron particle and a lot of energy. Yeah, lots of energy. I mean that's why it is the holy grail in energy production. But we should not forget that we need a plasma background. Like this whole reaction, the nuclear reaction happens in a plasma system. And but then, why is it so difficult? And it has not been easy. Why do you need scientists to try to solve the challenges? Because when it's a nuclear reaction, the nucleus are both positive for deuterium and tritium, and it's almost like pushing things up a hill, and they have to come very, 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 very close together to even fuse, like in the order of femtometers. But how can you do that? What increases the probability of doing that? One is you can increase the number of ions in the plasma, which basically it's the density. You can increase their temperature because the faster they move, the closer they can approach. And on an average, that is basically their a sense of kinetic energy, the sense of temperature. And it's amazing that we can, as a human species, as a group of scientists, produce like 10 times hotter stuff, like 10 times hotter than the center of the sun in a magnetic bottle effectively, right? So higher density, higher temperature, but that is not enough. We need to actually sustain the higher density and higher temperature for long enough. And hence we actually, I say it is the like tripartite kind of struggle, three forms that you need high density, high temperature for long enough time. And this is called the Lawson criteria. N, T, and tau. All three must come together. The product of the three has to cross some threshold, and hence then we will be called burning plasmas. It's almost, in a fun way, it's like triathlon. Like you cannot be the fastest swimmer or biker or runner. You have to be good in all three to win a triathlon, award. And so how do we do that? How do we sustain this kind of a plasma? We use in today's talk, that's what we are, most of us are from that background. We'll use magnetic confinement. And it's almost like you have magnets shaped in the form of a donut and, well, a plasma filled donut, which is similar to a jelly filled donut. And you don't want that jelly to strike the wall and come out, right? That would be bad. And in that sense, you might ask like, so what work has been done in the previous years and where are we now? It's the progress in fusion science has been amazing over the last many decades. The progress is faster than memory chips that allows cell phones and laptops. It's faster than the energy production of large hadron colliders. And there have been many, many, many efforts on different fronts, not just magnetic fusion, inertial fusion, magnetic fusion, different kinds of techniques, experimental techniques, and theoretical advancements, which are bringing us closer and closer and closer to fusion. And we are kind of there, almost there, but not yet, because some challenges are still there, which we are working on. And so a couple of things is wonderful. In green, I have, we can reach good enough plasma density to achieve fusion. We can get amazing temperatures, 150 million degrees centigrade. It's not a joke, right? Of course, I think. the other thing is like, can we hold in that state for long enough? That is what we are now working with. And as we are working with that and coming very, very close, in some instances, we have actually achieved, the threshold of Q is equal to 1, which is the energy input to energy output. But then other problems come up that if you hold it for long enough time, is it good? Can we scale it up? Can we make it commercially viable? Or do we have other issues? So, and that's why, this picture of me is like, I'm always confused and questioning myself and also very thoughtful. So these are the things, right? That the hot and dense plasmas can be very unstable. You have waves and particles and filamentary structures and intermittent structures coming in, and we will be talking about that, the details of that. The certain modes of plasma operation can be better than others. The plasma has this property of self-organizing itself into different states. And we will also be talking about that. Now, if they are so hot and dense for long times that commercially fusion becomes viable, then will it damage the material container? Because now you're holding it for way too long, right? And so we'll also talk about that. In that sense, this is what again, there are students in here, and we will be using some terminology. And you can say the very hot, dense, warm plasma is at the very core. We call it core plasma. Surrounding that is colder plasma. It's not really very cold. It's still much, much, much warmer than room temperature. But that cold plasmas have different characteristics. Then we use these things called diverter to divert the very, any kinds of ash, which is the helium gases. And so the diverter diverts things. And the scrape-off layer is the thin layer between the warm plasma and the cold plasma and the actual wall, the material wall of the container. And all of them have their own issues. So plasma self-organization itself is the shape of the plasma. What is the mode of the plasma where which fusion will happen? The wave-particle interactions makes some things worse, and we will talk about that. We have instabilities in the system. Then when the plasma hits the wall, plasma material interaction becomes a big deal, and it can produce dust and debris. And just like a grain of sand in my food doesn't feel nice, so even a grain of dust might be bad for fusion. So with that, I'll go back to Noah, and I'll forward his slides. Just let me know. So Noah, take over from here.
Oh, thanks, Saikat, for the nice introduction. So I'm going to be talking about self-organization. And so this is a process by which physical systems, including plasmas, can sort of spontaneously generate their own shape and structure. This happens in all sorts of plasmas, and in particular, it's going to happen in plasmas at the core of fusion reactors. And so it's very important for us to understand how plasmas organize themselves in order to have success with nuclear fusion. Next slide, please. Okay, so I'd like to start by discussing the second law of thermodynamics. This is the tendency for entropy to increase over time, or the amount of disorder in a system to increase over time. So for example, this cup of hot coffee sitting on a table will over time equilibrate with its surroundings. And we will go from a structured state where the coffee is hot to a sort of featureless state where everything is at the same temperature. So the second law moves us towards featureless, structureless sort of uniformity. Next slide. But in fact, when we look around us, we see plenty of things that are very structured and very ordered. Like this cat here, this is Kermit. And so how does something like Kermit arise in the presence of the second law of thermodynamics? Well, actually, Kermit is able to lower his entropy, S1, and maintain this low entropy ordered state by increasing entropy elsewhere in the universe. So he interacts with his surroundings in order to increase S2 such that the total entropy increases. And this is basically how life is able to exist. And Erwin Schrödinger put this very nicely by saying that living matter evades the decay to equilibrium by feeding on negative entropy and extracting order from the environment.
Yeah.
Next slide, please. Okay, but it's not just living things that do this. In fact, like relatively simple sets of equations can yield structure from featureless initial conditions. I have a few examples here. The first is the spontaneous generation of vortex crystals in a pure electron plasma. So this system is going from something that's very disordered to something that's ordered over time. And it does so by increasing entropy elsewhere in the plasma, basically. Another good example is the zonal flows or the banded pattern that arises on Jupiter and other planets. And then another good one that's going to be relevant here is self-organized criticality. This is a picture on the right of a sand pile in my backyard. And in fact, I can continue to pile sand on that pile, but I have no control over the slope of that sand pile. The slope is determined by the physics of gravity and the sand. So these are examples of natural systems that are choosing their own shape. There's another good one called Turing patterns, and I think maybe Elon Price is going to talk about this, so stay tuned for that. Next slide.
Yes.
Okay, so let's move on to toroidal fusion plasmas. And I'm going to make the case that self-organization physics in many different types of fusion plasmas has a very important impact on fusion rates and fusion performance. So I like to show this plot where I'm showing a spectrum from left to right, where on the left we have things like the stellarator, where we create all of the magnetic fields externally, and the plasma has somewhat less freedom. We're exerting more control over the plasma. On the far right, we have so-called self-organized configurations, including the reversed field pinch, where essentially we just drive a current through the plasma, and then the plasma generates its own magnetic fields. So the plasma has somewhat more freedom, and self-organization plays a stronger role. Tokamak, in fact, is somewhere in between. So we create part of the magnetic field, and then the other part is generated spontaneously. Next slide. Okay, so let's think about this. In a fusion plasma, we're putting in heat, we're putting in particles, and we're driving electrical current through the plasma. But in fact, the plasma winds up deciding how to distribute these things in the radial coordinate, moving from the plasma core outwards. So the plasma sort of selects its own pressure and current profiles. In some cases, we have some control, but in fact, self-organization plays a strong role here. Even in a case like the stellarator, where we're actually not driving any current through the stellarator plasma, the pressure profile still behaves like this. Next slide. Okay, so now I've blown up this picture of the profile. I hope you're able to see this. And I just want to make the point that there's all sorts of different physics that impacts the shape that these profiles take on, and these are very much active research topics. Without going into great detail, we have things like sawteeth, which tend to flatten the core profiles. We have turbulence, which tends to set a critical gradient in the plasma, very similar to the sand piles. We have H mode, which was one of the major successes of fusion research so far, and involves zonal flows, very much like Jupiter. And then we have things like edge localized modes, which are related to a critical gradient right at the edge and can be very damaging to a fusion reactor, and also disruptions in which the magnetic field becomes stochastic or random and can also damage the fusion reactor. All these things are, there are papers coming out about all of these topics every year. Next slide. Okay, so just to wrap it up, I just wanted to speak briefly about what I do. I work at the Madison Symmetric Torus, and we can make different types of plasmas, the reverse field pinch and the tokamak, and this type of plasma called ultra-low Q, which is sort of between those two. And we study all different types of self-organization. In fact, we're the only machine in the US that can make these RFP and ultra-low Q plasmas. So it's a very unique device. And the one that I wanted to highlight here was the spontaneous generation of these helical states. So these are helical states that arise naturally from otherwise symmetric plasmas, and these break the toroidal symmetry. And so we're trying to understand in each one of these different configurations how these helical states arise and how robust they are, and so on. Next slide. And that's all I've got. So thank you very much. I guess we'll pass it on now to who's next?
Yeah, I'll pass it on back to Eva. And here are your slides.
Hi, so I'm just going to give a brief introduction into energetic electrons, and then we'll pass it on to Sydney and Jessica, who are actually going to talk about how do we study those in magnetized plasma from lab to space, and how actually those two fields really inform each other. So next slide. Energetic electrons form in all plasmas. So they are characteristic for space, for low temperature plasmas and technology, and especially in fusion energy. In fusion plasma, you'd expect the electrons to be already pretty energetic because, as Saikat said, the temperatures are so hot and the densities are high. However, a fraction of these electrons can become even way hotter and way more energetic, and their speeds reach close to the speed of light. So now those are called energetic electrons or runaway electrons. And you can think about it, they call runaway because they're really hard to confine into the magnetic confinement of a tokamak, as you may see here in the illustration on the right. But you can think about it also, imagine if you have like a highway with very fast cars, and then a subpopulation of these cars all of a sudden start accelerating to jet plane speeds. Naturally, if the highway twists or turns, does anything, these are going to drift massively and leave the highway. So next slide. Now, this kind of an illustration of like a very first principle picture of what is going on. Why is this possible? So at the very base level, we can think of it the following way. The two processes, that one of them is collisions and the other one is acceleration due to electric field. Collisions are processes where when particles collide, their motion gets randomized and that kind of slows them down. Versus whenever charged particles are in external electric field, they'll feel electric field force and accelerate due to that force, because force equals mass times acceleration, right? So every time there is electric field force acting on a charged particle, the charged particle will accelerate. Now, it's the competition between those two processes that may result into the acceleration winning if the collisions are not efficient enough. And actually, it's kind of like if particles are just a little bit more energetic on average, then they tend to miss each other and really collide inefficiently, which leads them to be accelerated even more, and that makes them even more collision-less. So it's kind of a stage process. So you're going to think, okay, collisions versus acceleration, physics has figured out. Well, collisions are not very straightforward processes when you're talking about plasma particles, because the interactions between charged particles act at a distance. They don't just collide like billiard balls. They really scatter, and the way they do this changes the landscape of all the other particles around them. So it's actually not trivial to model collisions in such a system. Also, electric fields can arrive in one out of bajillion types of processes in fusion plasma or in magnetized plasma. So actually, while it all comes down to this kind of competition, the actual physics processes that can lead to collisionality or electric fields, local electric fields, are not straightforward. Next slide. So why do we care about these energetic electrons in fusion plasmas? Well, on one side, so what you see here is a visual, this side. What you see here is an image of actual damage done by a beam of energetic electrons hitting the wall of a fusion device. This is the jet tokamak. And as we said, if those are very energetic, they tend to be very easy to lose from the plasma. And especially if there is something like a plasma disruption where the magnetic field starts collapsing, they hit the wall as a beam and deliver all of this energy onto a location on the wall. So this naturally can damage the walls. It can punch through materials. It can limit the lifetime of components used for the walls of these reactors. So it's very important to understand how are these particles generated and how to control them for a stable operation of fusion machines. Next slide. Yes, and there are specific questions. I mean, honestly, it's a zoo of physics, fundamental physics questions. How exactly do these energetic electrons form? So what processes lead to these accelerations? And then why do we see them in these very big numbers during plasma disruptions? Based on the physical process that drives these electrons, what is the maximum possible energy that they can have. And there indeed different processes can increase the energy by to a different threshold, but then there's a minimum threshold of energy that electrons need to have for the next process to pick up. So actually these processes, some of them you're probably going to hear about from the space talk, the space plasma talks, but you have magnetic connection, interaction with waves, interaction with turbulences, all of these processes. And of course, we're also going to discuss a mirror effect when they interact with magnetic field structures that work as magnetic bottles. So all of these processes are a different direction of physics research, and all of them very likely happen in a tokamak at the same time. So unpacking that physics is very difficult and very interesting. Next slide, please. And I'll lead here before I pass it to Sydney and Jessica. But curiously, you can same processes lead to the generation of energetic electrons in near Earth environments. So in the Earth's magnetosphere, so the layer, the extent of the Earth's magnetic field around the Earth, actually spacecraft observations directly link the solar activity to the occurrence of these energetic electrons that get trapped into magnetic field structures in the Earth's magnetosphere. And when they get accelerated beyond a certain threshold, they can escape the magnetic field and penetrate into the Earth atmosphere. And this is where we get geomagnetic storms, when we have satellites and aircraft breaking of communication. This also creates very dangerous conditions for astronauts. So actually, there's a huge question in space weather. And what's amazing is that spacecraft measurements gives us very unique picture of how the distribution of energy for these electrons look like, which actually help us identify what is the physics, while we go back to fusion devices where we can actually reproduce some of these conditions in a controlled way and test the models that we've developed from space observations. So with this, I would like to pass it along to Sydney and Jessica, who actually each one of them deals with this problem in two different environments, fusion reactors and Earth magnetosphere.
Ooh.
Okay, so me and Jess are going to kind of split up our section of the talk, but if you'll actually go to the next slide real quick, I am going to kind of touch base over what Eva just went over. So kind of the motivation behind what we're looking at. Obviously, introductory electrons affect fusion plasmas as well as space plasmas. I mostly focus on space plasma, so that's, like she said, geomagnetic storms, that's affecting satellites. I'm sure you've heard a lot about like solar flares and taking out, the grid on Earth and everything. So this is kind of what this research is contributing to figuring out. And so specifically what I will be looking at, or what me and Jess both look at, are energetic electrons interacting with magnetic islands, which I'll go over in just a second. But the main goal is to really figure out what processes, like plasma processes, will scale from lab to space. Because at that point, we're looking at more fundamental plasma processes. And so if we understand one in space, understand one on Earth, hopefully we can join the two. And that's kind of the point of our interdisciplinary work. So you can go to the next slide for me. Okay, so very brief, simplistic overview of magnetic islands. So really what these are whenever they occur with magnetic reconnection. So this is a process where the magnetic field lines will kind of break and reconnect, and they form these like loops that you see on the top right. And so this is what actually accelerates the particles, and then because it releases magnetic energy as well whenever they snap and break and reconnect. So in Earth's magnetotail, which is you can see in the bottom right, magnetotail is just like the dark side of the Earth, and so it's like at the end of the magnetosphere. So that is where we get like auroras and things like that, and then Jess will go over more what happens in the D3D side. That's what magnetic islands are. So we have what we'll refer to as O points. That's just the center of the island. This is where the plasma is getting trapped. And then the X points are the edges of the island. And this is where we expect to see energetic electrons. And so this is whenever they're, splitting off in the tokamak and they're hitting the walls, and this is where they're escaping the magnetic field lines in space and starting to cause all sorts of trouble. But we'll kind of reiterate over and over again. X and O points. It's going to be the center and the edge of the islands. And go to the next slide for me. This looks a little scary at first, but I really wanted to highlight the difference between the data between MMS mission, which is the spacecraft I look at, which is magnetospheric multiscale mission from NASA. The data is going to look very different, but we're still seeing the same processes. So, starting with the probably prettiest one to look at is the top right. Where you're looking at is actually a density of electrons. So whenever you see that dark red, that's where there's a lot of electrons gathering. And you can actually see this magnetic island structure. And I have it, the middle of it is in the dotted lines, and then the X point regions are in the solid lines. So, we'll see like a lot of plasma gets trapped, and you see that big red blob, and that's the center of the island, which is what, we would expect to see based on Earth experiments. And then in the bottom right, again, kind of gross to look at, but this is where we actually see energetic electrons, and we're starting to see them peak at these X point regions. Um, and then the way we actually find these, because space is huge, and Eva made a really good analogy of the MMS spacecraft as like a bug on a mountain, trying to figure out where all these little magnetic islands are happening. So we don't see everything going on all at once, but we can look for what we call bipolar BZ signatures. And all that is we look for when a magnetic field reverses. And so we'll see in the Z direction, for example, it has that dip and then peak. That's in the top left graph. And so that is indicative of a center of an island. And then we also see an increase in density, which is in the bottom left graph. We'll see a lot more electrons are gathering at this O point, and then we start looking around that region and kind of piecing it all together. So it's kind of like getting individual puzzle pieces, and then we put it all together, and we're like, okay, yes, that is a magnetic island. We're looking at where the electrons are gathering, where they're most likely at, their velocity, so we can see how energetic they are, things like that. So that is the very brief overview of the space side of things, and then I will let Jess take over what we see in D3D data.
Okay. So in D3D, we can actually create these magnetic islands using different coil contributions. And in particular, what we can do is create like this 2-1 island and then bifurcate it into a 4-2 island. So on the bottom left, we have this 2-1 case that has 2 O points and 2 X points. And then on the right is the 4-2 case that is created around like the same radial location, and it now has 4 O points and 4 X points. And so this island bifurcation, we get it from rotating these coil contributions and then causing modes to cancel out this like dominant case to the next dominant case. So this bifurcation reshapes O points, X points, and the separatrix, which is the line around the island, really. And this, I don't know what just happened on the screen. And this modifies the electron transport, because what we've also seen in these experiments that we've done on D3D is that energetic electrons get trapped within the islands themselves. So we see at O points that there's trapping of these energetic particles, and at X points, these are like escape point paths where they're able to be released. So when you cause a bifurcation of the island, you're also allowing for an amount of this population of energetic particles trapped within the island to be released. So this kind of provides like a scalable way to mitigate these energetic beams that we saw destroy the wall of jet from actually just going on one way. We can like leak them out periodically. Next slide, please. Okay, and the way that we can do that, well, the way that we can understand more of what's going on is using different types of modeling. So what's shown here is how we've used this code TRIP3D, which is it was a magnetic field line tracing code, which takes in the plasma equilibrium reconstruction that's calculated with this code called EFIT, and then the actual currents from the coils from experiments. And we can create those vacuum reconstructions that we saw on the previous slide, but then by adding a particle tracer to this code, you can actually simulate collisions between these background electrons. So we can get an idea of just like how electron diffusion is happening at the basic level. So not even with like the energetic particles. And we could get these nice diffusion plots, which you can see in this top figure here, where this is when we were starting some particles from some tracer electrons from the X point, and you can see how they like diffuse out in here. And then we can also reconstruct histograms from final positions to see actually what type of regime is happening for the diffusion. And what's not shown here is we can also look at the energetic population and how they're being affected. And for energetic particles, actually like drifts are something that's more important for these things because there's contributions from electric and magnetic fields that will cause these electrons to be pushed and move differently across magnetic field lines instead of staying so like closely confined. So we can also do that it's a code called MAFOT. But yeah, I think next slide. Oh yeah. So
Yeah.
comparing across D3D and MS data shows that there are these electron and island interactions where you can see that bulk electrons are trapped around O points and they're found at X points of the island. It also can be accelerated out from these X points, and also island width, it determines the maximum energy of trapped electrons, which has been seen both in lab at D3D and also in space.
Oh, thank you, Jessica. And now back to Yashika. So from Jessica to Yashika. Cool. And yeah, take it on.
Okay, all right. So I'll speak about the wave-particle interactions in fusion plasmas. Next slide, please.
Oops, sorry.
So, no worries. So, wave-particle interactions occur whenever the speed of the charged particle becomes very close to the speed of the wave that it's trying to resonate with. So, it's very easily understood by a common picture of a surfer riding a wave. So, basically, when a surfer has a speed slightly lower than the wave and it wants to go uphill the wave, it basically gains energy from the wave and the wave damps. And when the surfer wants to go downhill, it basically gives some of its energy to the wave, and the wave basically increases in energy and the surfer's energy damp. So this process of resonance between the particle or, the surfer and the wave, and which is very analogous to a charged particle and a plasma wave in plasmas. So this picture is called Landau resonance, and based on the distribution of the particles, for example, in this figure here, which shows this distribution function, and this basically tells us the number of particles per unit volume that have a particular speed. So if the particle speed is very close to the wave speed at this VPH or V phase, or which is the phase velocity of the wave. So if the particle has speed very close to the wave velocity and the particle has a velocity slightly slower than the wave, the particle is going to gain energy from the wave. And if the particle has energy slightly greater than the wave, it's going to give its energy to the wave. And in a distribution like this, where we have these positive gradients, the particles gaining energy from the wave are low and the particles giving energy to the wave are high. This drives a particular wave unstable. And this can be good or bad based on the wave and particles we are trying to look at. For example, for Alfven waves and fast ions, these are basically very harmful. And for Whistler waves, runaway electrons, which I think a very nice segue has been provided already. So it can actually be good. So I'll start by speaking about the Alfven waves. So Alfven waves have been first observed by Hans Alfven in solar plasmas when he was trying to predict the issue of this anomalous solar coronal heating. So, but in fusion plasmas, due to the periodic conditions imposed by the machine's geometry, Alfven waves exist as Alfven eigenmodes. So, Alfven waves are generated whenever there is a perturbation perpendicular to the direction of the magnetic field lines. And in fusion plasmas, this is a schematic of an experimental fusion device that's being built in France called ITER. So in a fusion plasma, you see these blobs here. These blobs are indicating the perturbations of Alfven eigenmodes. And these circular lines, they are actually indicating fast particles, which can be the fusion bond alphas or the neutral beam particles, which are injected to heat the plasma to very high temperature, 10 times the order of magnitude as compared to the core of the sun. So these energetic particles may interact with these Alfven eigenmodes, and in turn, the Alfven eigenmodes can transport them, redistribute them, or lead them to loss. So these can be lost out of the main plasma, and the consequence of that is that they reduce the self-heating efficiency of the plasma. We want these energetic particles to stay long enough within the plasma that they can give their energy back to the thermal plasma, and the plasma reactions keep on going, and we achieve burning plasma conditions for a very long time, which is the steady state. So if these particles are being lost, the self-heating efficiency of the fusion device is reduced, and which hinders the economic viability of a fusion device. And then once these particles are lost and they hit the wall, they can also damage the wall or the diagnostics in the wall, which is again something to be considered when we are considering the overall cost for building a fusion reactor and operating it. So it is very important to study in what regimes, how much is the transport driven by these waves, and whether that's permissible or not. So we do modeling in order to identify those operating scenarios, a set and parametric regimes where these waves are not harmful anymore and they don't transport enough particles to reduce the performance of a fusion device. Next slide, please. Okay, so the next kind of wave particle interaction is between Whistler waves and runaway electrons. And as you saw, these melt pools that were generated in D3D due to runaway electrons formed after disruptions. So Whistler waves can actually be intentionally launched in order to mitigate the energy of runaway electrons. So that's an alternative mitigation strategy. One of the mitigation strategy was talked by Jessica. So this is an alternate to that. Actually, Whistler waves were observed in space plasmas first. And if you do a quick search on YouTube on Whistler waves, you can also listen to the whistling sound which these waves produce and which has actually led them to their name. So these were infusion devices in tokamaks, actually in D3D. In 2018, first experiments were performed, which were specifically to detect the Whistler eigenmodes or Whistler waves, and trying to make a connection between the space plasma and the fusion plasma physics. And hence, once we observed that the Whistler waves are actually able to scatter the runaway electrons in pitch angle, we actually thought of using it as an alternate mitigation scheme, because when the Whistler waves scatter these runaway electrons in pitch angle space, it increases the perpendicular velocity component of the runaways and hence also increases the synchrotron radiation that these runaways emit, which can dissipate a lot of energy of the runaways, and they don't cause those intense melting of the plasma reactor wall, and don't act like a welding torch almost, which can cause a damage not just the plasma wall but to the components behind the wall as well. So we do a lot of modeling. We calculate these Whistler fields. If you can press one more time. Yes, thank you. Yes, this one. So we do a lot of modeling where we initialize distributions of runaway electrons in energy and pitch angle space. And after a particular time in the simulation, in the presence of Whistler fields, we observe how these runaways are scattered in pitch angles. And generally, from our observations so far, we have seen that these runaways can be scattered to very large pitch angles, which gives us hope that we can probably use this particular mitigation scheme to eliminate some of the damage. In this case, for Whistlers and runaway interactions, these were actually useful for us to mitigate some of the damage, but for Alfven waves interacting with the fast ions, they were actually not very good. These connections needed to be made, and so from space, we were inspired to do these studies in fusion plasmas, this was very illuminating. And I'll stop here and I'll let you go to the next. Yeah.
Thank you very much.
I'll share my slides.
Okay, so I will stop sharing.
Yeah.
Okay, and then let me make you a co-host, so I think it becomes easy to share slides and
Yeah.
So can you check if you?
Yes, I think I can share now.
Cool.
Yeah. Yeah, thank you for letting me in. Yeah.
Yes. Oops.
Oops, sorry. Okay, just let it be like this. Okay, you can see my slide? Hello?
Yes.
Yeah.
I think yes.
So yeah, so I'll be talking about alpha wave and arch plasma relevance for the fusion research. Thanks for Yashika for explaining and lessen my burden for explaining Alfven waves. Um, so here you see the picture. This is the picture of arch plasma, which I'll be talking about soon. So as you know, that Alfven waves are low frequency magnetohydrodynamic waves, and they have a very important role in the fusion devices as they hinder the fusion confinement. I just want to add here that in related to the fusion devices, they have a very major role in the heating of the solar corona, and they have been mystery for been years. And you can study these kinds of wave and the Alfven wave interactions with the fast ions in separately in other devices. And one such device is large plasma device, where you can launch these waves and see the interaction of these waves with the fast ions separately. Next, I will move on to the arch plasma. So basically, arch plasma is formed between two electrodes. They are high current structures, and they can be acted as similar to, like in tokamaks, you have this curve-shaped plasma. So this you can create in the laboratory. We have this solar plasma device at UCLA, where we have this arch plasma setup. So on the right, so this is on the bottom left, you see the picture of solar plasma device. And inside we have this electrodes from which we create the arch plasma. And here you can see the eruption of jet coming out of the arch. So what happens is, like, there is an external magnetic field going into the page, and this external field causes a disruption in the arch, which causes the eruption. While when we have no magnetic field, the arch remains stable and uniform. So you have like a controlled arch in the device, which you can form in the laboratory and study what type of modes present in the plasma and how the arch is evolving. And these skiings are also relevant to the fusion plasmas. And also, like the how the reconnections are happening, field lines bending, and the magnetic topology, which is important for the fusion studies. And there was an experiment where in the same device, where they explained that the formation of stability of arch plasma loops to analyze how structures evolve and interact with the magnetic fields, and they are critical for the fusion plasmas too. That's all from my side. Thank you.
Okay. Thank you. Then let me re-share my slides, and I hope. Okay. Can you see my slides?
Yes.
Yes.
Okay. So this now I get a chance to go back to Elon, and Elon, you can introduce yourself and then start talking about your research.
Yes, for sure. So, can you guys hear me okay?
Perfect.
Okay, awesome. So, hey everybody, I'm Elon. Happy Fusion Energy Week. I'm really excited to talk a little bit about my work today. So I am a fifth year PhD student. I'm actually going to be going into my sixth year next fall. And I have been working in the Magnetized Plasma Research Laboratory at Auburn. And as you can see here, we have this huge device. It's about 1.57 meters long. And sometimes I stand on top of it. It's really tall. And it is called the Magnetized Dusty Plasma experiment. Now, we are known for doing dusty plasma low temperature experiments. So take your temperature down for now, because we're in the low temperature now. But in my work, I'm actually looking at the dynamics of the plasma itself without dust. And so we're going to get into that in the next couple of slides. So these are just some values here that are just showing you what regime that we're in. But long story short, we're looking at low temperature and high field that corresponds to the edge of fusion reactors. So this is a very, very strong magnet. So here I'm showing you what results when we put that low temperature plasma in and we slap it with that extremely strong magnetic field. And as you can see, they're not just shaped weird, they also move weird and they wiggle around and they're very fluid-like. And so this is a very interesting phenomena that we have access to and that is actually quite reproducible. And just a quick aside, these are three-dimensional structures. So there you're also seeing a side view of these plasma columns that are in between our two capacitors. And so these structures start to form in a more coherent way when we get above a field that's 1 Tesla, which is very, very strong if you're not familiar with Tesla. So what we've already known from all these past 20 years is that the type and the number of filaments that we're observing is determined by how magnetized we are. In other words, how strongly are the particles in the plasma orbiting our magnetic field lines before they collide with a neutral particle. And so that will tell you how strongly magnetized you are. And the more magnetized you are, the more weird wiggly arms that you get, essentially. And so you can already look at that video and see that there's some arms popping out there. And one more thing before I go on to the next slide is that you can have filaments going everywhere in a sort of unconfined region, or you can just slap a copper ring on the bottom electrode, quite literally, and you can trap the filaments inside of that area. And you may be thinking now, okay, that's cool, but like, why would you want to do that? Well, the most amazing thing about doing this type of research and so easily imaging it and recording data is that we can do tracking with it. And so on the next slide, I have some examples of what I've been doing over the years to try and not just quantify the type of dynamics and filament motion that we have, but also to extract a metric using machine learning tracking techniques and maybe even AI. And so this really opens up a door for research where we can do different types of things and gain information about what are the underlying physics that's driving the emergence of these structures. And as you can see here in that tracked video, the tracking works pretty well. And this is actually an open source computer vision software through Python. So there's a lot of resources for it. And as someone who struggled with computational for a little bit there in my undergrad, it was actually not bad to learn. So if you're interested in becoming better at coding, this type of research doing image analysis is a great way to do that. And furthermore, since we are in the same magnetic field regime, there's a connection there, but more importantly, there's a connection with this idea of using image analysis to track structures like blobs at the edge of fusion detectors, and the kinds of physics that we can extract from that to reveal what is driving this transport, which, as Noah said earlier, can be very scary and dangerous. So I'm very excited to see where this research goes in the future, and I hope that one day it'll also help us answer fundamental questions about theory for how these structures are formed. Thank you, and let me know if you have questions.
Yeah, I might go back to Eva now again for dust and debris in fusion plasma.
Okay.
Yeah.
Well, there's a nice introduction that Elon made to tell you how complicated this environment is, where the plasma of a fusion device has to meet the wall. So it's going to be a lower temperature plasma, but highly magnetized, and it's going to have all of these complicated structures that Elon's talking about. And now on top of that, we're going to add dust and debris, so flying chunks of material from the wall. Sometimes they generate from the plasma. They can get sucked into the core, contaminate. So what is a dust in fusion? So fusion plasmas are and will be and will always be inherently very dirty environments because they need to be confined into walls, and they have to operate consistently for long periods of times. As a result, it's very well known, even for research level fusion machines, that the walls themselves are going to produce a bunch of dust and debris due to multiple processes, including erosion of the wall, melting of material during plasma disruptions, flaking, redeposition of material back to the wall. So in any one of those cases, the first thing that happens is these particles. So here on the right, we see examples of actual images from different material types and shapes that have been analyzed from different facilities. Those particles will be light enough. So you see they're micron size. So this is like a fraction of the thickness of your hair. So they can be picked up by the flow, they can be carried around, but they also have gravity and they also can charge. So now they can become like this really heavy plasma particle in a sense that interferes with the plasma environment. So next slide. This is a very complicated problem because there is a multitude of processes that happen that are relevant and they kind of feed each other. So this is like broad splitting the questions into four broad categories. So on one side, what processes generate this dust and debris from the walls? What are the sources and what are the rates at which this dust will be generated? This is going to tell us, okay, how frequently we need to maintain swap elements from the wall. How can we clean this? How often this dust need to be flushed out of the machine? So as we said, there could be multiple processes that generate them. Then the next thing is how do these particles charge? So dust particles charge by the straightforward process will be direct collection of electrons and ions on their surface, but also they can be the charge can be affected by the background magnetic field, which affects the electrons and ion populations. It also can be affected by interaction with different electromagnetic waves. So it's a very rich question. And now that the particles is charged, then those particles are subject to a variety of forces due to the electromagnetic fields in the plasma, but also due to the fact that these are massive macroscopic particles, so gravity acts on them, drag forces, flow forces, thermophoretic forces, all of those can act on these particles. So what are the relevant forces and how do we model those? And then finally, and this overcomplicates everything, these particles, when they get into this hot environment, their morphology changes. They can ablate, which means they can lose mass from just a disassociation of the material, which changes their shape, which changes their charging, which changes their way they interact with forces, which changes where do they go or where do they get deposited. And one of the main huge needs right now is to establish under what conditions, so put all of this together, under what conditions are these particles going to accumulate somewhere and become permanent source of impurities for the plasma, or be sucked into the plasma, and then be the full dissociation of these materials into the plasma is going to suck energy away from the plasma core, and therefore leading to a disruption of the plasma. And this is obviously not what we want for sustainable operation of the fusion power plant. Next slide. So these are very specific. So actually, I really like this image from this 2017 paper. It's because it looks like those are these like blobby monster particles. But what the study was trying to show is that on one hand, so the particles can coagulate and grow on the wall of a fusion plasma, and depending on their size and the properties of the flow, they can either adhere or be swept into the plasma. And now, why is this a huge issue and needs to be understood better for fusion? There are multiple reasons. Some of them include fuel retention. So for example, we know that deuterium and tritium are the most popular candidates for a fusion reaction for these power plants. Tritium is radioactive and it tends to compile into materials. So we need to understand how tritium is going to get trapped in this dust and debris particles. The plasma contamination, as we said, if these get sucked into the core, their dissociation is going to lower the temperature. And as you heard from like Sayakat introductory talk, by the time you lower the temperature, you drive down the Slowson criteria, you can lose the plasma. They also cool the plasma through radiative cooling, and they pose risk of disruptions. They also in general modify the profile, the densities and temperatures and flows of the edge plasma, and they can also damage things, right? I mean, it's a flying particles that can be swept into a diagnostics port and damage a device. Next slide, please.
Sorry, I don't know what happened. Okay, now you.
Okay, yeah, because
you
this
just
video probably took a little bit of time to load. So as Elon pointed out, one of the best ways in research facilities to study these things in detail is to use cameras. Camera data is very heavy, and it's very hard to store. And cameras are optical instruments that are very hard to maintain in a aggressive environment, such as a fusion power plant. So actually what we're trying to do is use this infrared cameras, visible imaging cameras, multiple cameras to really understand these particles in research machines and then model where did they go, what did they do, and how are they going to lead to signals on other diagnostics such as spectroscopy or diagnostics used to monitor plasma temperature and density, because those will be the ones that will likely be there in power plants. So it's a very important bridge, this image analysis to maximum utilization of information from these cameras on these research facilities to help us understand where did the particles go. So those are two videos from the D3G tokamak, and you can see there's actual experiments where we introduced dust particles in a control way into the plasma and then observe where they go. And as you see on the right side, there's a kind of tangential view of the tokamak, and you see one of the pellets that was injected was split. The other one kind of like glows real bright, which is an indication that it starts ablating. And if we go to the next slide, what's very powerful about doing that kind of study in fusion research facilities is that we can inject the particles deep into the core of the plasma, in which case the conditions, the plasma gets so hot that the heat flux to the material typically exceeds the material strength, and you see what's called spallation. So when the material starts uncontrollably throw these shards of material instead of just atomically lose mass through something like sublimation. So this is actually very interesting because, and I'm going to end up with this, as everything else that we mentioned, fusion is very interdisciplinary. And this plasma material question as well is very interdisciplinary, because while we're trying to study how material changes the properties of the plasma, if it gets into the plasma, we also study how material performance in extreme conditions, which is actually relevant beyond fusion to aerospace, to all sorts of to nuclear fission reactors, to all sorts of environments where we anticipate that materials need to withstand very extreme conditions. So with this, I'm gonna pass it to the next
back to someone called Saikat. So thank you, Eva, for saying this. And I would like to kind of conclude in a very simple way that plasma material interaction, exactly as Eva said, like is an immense thing, because that could be the last frontiers that we need to overcome, so that things can happen. And then, well, at the end of the day, I'm already kind of hungry. So I'm thinking like, what, let's think, it's for every one of us to, what do we need to cook anything, right? Of course, the thing to be cooked, the heating system, you need to cook it, right? So the oven and the microwave. Something else is important. The utensil in which you cook, right? I mean, if you don't care about the utensil, it would be bad. I mean, I cannot cook chicken on my hand on a grill because my hand would not be a good utensil. Sorry, bad joke, very bad joke. But what if the utensils get damaged, right? In this particular case of thermonuclear fusion, we are trying to hold together something that is 10 times hotter than the center of the sun. which is mind-blowing, right? And we need multiple components to work together. There are plasma diagnostics. How do we measure things? How do we put the energy together? So how do we heat up the plasma? And so literally the plasma can damage the material around it, and the damage from the material can lead to all sorts of shenanigans, just like Professor Kostadinova said about production of dust and production of debris, which can now kill the plasma. So yeah, remember everything that she said earlier. And so this is just one example of the inside of a tokamak is extremely complex. Many components are there, right? It is many components, the heating systems. The diverter is a region which will be in direct connection with the hottest of the plasmas. The first wall, if something happens to the plasma, these little filaments that can come out and hit the walls. The energetic electrons, the runaway electrons that we heard about, they can come and hit the first wall. So they will be damaged, they will be cooked in a sense, right? And future tokamaks can be even more complex. We might need liquid lithium walls for multiple reasons. And in that sense, it's a very complex problem again. There's ion bombardment from the first ions. If ions get implanted into the structure, it can damage and change the structure itself of anything it is getting implanted into. Just the thermal heat fluxes are immense, not just the ion bombardment damage, but just from the heat. Things melt, right? When things are hot. There can be co-deposition and sequestration of stuff, and also the mechanical and properties will be stable under these thermal loads. And the longer we go, remember going back to the very first discussion how we started, we need hot, dense plasmas, but for a long time. The longer we go, the more the probability of damage to the components around the very hot and dense plasma, right? So these are very active fields of research. And I mean, I cannot do justice to anything, but I would rather point out that two conferences are held in every alternate year, one called Plasma Surface Interaction, PSI, and the PFMC, the Plasma Facing Materials Conference, where scientists all over the world are working hard on this, the fundamental aspects of how to take care of PMI. At the same time, we are building new generation machines to study PMI. And one of them is being built in Oak Ridge as I speak, the material plasma experiment. And in my previous job at San Diego, I helped that group in building the source for that plasma experiment, and it's being built. So in a few years, we'll be working there. And with this, I'll go back to Garima because she's also the chair-elect of the MagNetUS consortium. And with this, I'll ask Garima to kind of share her slides for MagNetUS and talk a little bit about that before we wrap up the whole thing.
Yeah, I'll share my presentation now. Hello again. So I'm showing my slide now. Yes. So in this talk, I'll be talking about MagNetUS. What is MagNetUS? So basically, it's a collaborative network that connects US labs and researchers to advanced fundamental magnetized plasma science relevant to fusion astrophysical systems. There are like many people involved in this. We'll know about them soon. So what are its goals? So basically, magnetized plasma shows up everywhere from fusion energy to space physics, but experimental research is often spread across many institutions with limited access to facilities. This creates barrier, especially to smaller programs or new research trying to enter the field. MagNetUS was created to address this by building a connected ecosystem, linking experiments, theory, and computation, while also focusing on broad participation and training the next generation. So here I'm showing the map, like these are the facility right now connected with the MagNetUS, and there are many more will be joining, some private companies and other research labs. Here, so MagNetUS started like in 2021, and we have now about 250 plus members. We have every year MagNetUS meeting where we share the results and the research in the facilities. And the next MagNetUS will be held will be in San Diego from August 3 to 6. We also share like quarterly newsletter. We highlights about the research labs and the results. Dimitri is taking care of that. We also have a webinar tutorial where we share a range of topics from machine learning, Python, plasma diagnostics. If any of you are interested in sharing your research, you're happy to talk about it. And we post it on the MagNetUS YouTube channel. So we have like many leaders and the officers working to keep up the MagNetUS. So currently I'm a chair-elect, Dimitri is a chair, and Noah Hurst is a past chair. So every year we have election. In the prior election we have these we have Ja, and from different facilities we have different people working for it. And this year elections are concluded and we have incoming officers. They will be leading the MagNetUS. And then next trip we will have election, and if any of you are interested, please you are ready to participate. And then how do you propose your experiment? Let's say if you want to do some research in one of the facilities. So every year we have a joint call for runtime proposal. This year, Steve and Senna at UCLA, he's handling all those stuff. So you can approach for the joint call using this link, or you can go to the MagNetUS website using this barcode or using the link. And or you can also approach to the different facilities and approach their directors that you want to do the research. Apart from these facilities, we are also welcoming the non-GE NSF facilities or the companies, those who want to join the MagNetUS. So how do you join it? Like there's a website, you can go there and become a member, and then there's like all sort of stuffs. And if you have any idea, we are welcome. We welcome you all to share. Thank you.
Cool. That was a very nice, and I would thank everyone to still stick with us together. We know we are over the hour, but these were so passionate, amazing talks that I did not want to shut down or stop anybody. But please, for everybody, this is a chit chat thing. You can ask us any questions, and it need not be necessarily about gory hardcore physics. It could also be about if a student is interested in internship opportunities, what to do next, or anything. Just go for it. What is it called? Open mic, open session. Yes.
Okay, I'll stop sharing now.
Sure. Thank you. Yeah. I mean, you can just unmute and ask something or raise your hand.
Hi, good afternoon.
Hi, Casey.
Hi, how are you? So I am Casey Price, mama to Elon, and I'm also an educator. And as a K-12 teacher, I see all the time students getting excited about space and energy, especially in lieu of what's just been going on with the latest missile launch. But plasma and fusion can sometimes feel very abstract. What is one misconception about plasma or fusion you wish that we would stop teaching early, and what should we replace it with?
Yeah, no, well, that's an amazing question. Thank you for asking. Well, actually, I can actually point out Eva also. We have gone to different student and teachers meetings, different science workshops, science fairs, and stuff like that. And I think the biggest misconception is plasmas are something that exotic that we cannot talk about. Plasmas are actually as complex or as simple as solids and liquids. I mean, we talk about them all the time. The properties can be very difficult. Just because they are rarer on Earth and associated with high level, high scale science and industries, it seems they are very difficult. But I think what we don't do as scientists enough is going out to the public, reaching out at a lower level. We have come out. So Eva's PhD student Jessica, who also talked today, Jessica, Eva, me, we came out with modules where you can, in a very fun way, teach concepts about plasma physics to middle school students, to middle school teachers. And these are modules we can share with you if you're interested. And Eva, you can come in and talk about a little about your plasma net.
I think just to build off of this, I guess like one main thing is that so what an educator can do is just call plasma when they see it. So we think it has been historically a difficulty that, the word plasma means plasma in the blood, and this is what students typically think of when you say plasma. Also, NASA, while they have this amazing education resources, they don't call plasma. They say black hole and
Solar wind.
sun and this.
Solar wind is plasma.
Right, astrophysical object. So basically, I think if there's one thing that we want to change with priority is precisely to battle this misconception that plasma is rare. So plasma is everywhere, most preferred form of matter in the universe, and students already know about it because they've talked about the sun, they've talked about stars, they've talked about it. So I think tying plasma to astrophysics and also fusion, right? Because this is one of my favorite things to do when I give outreach talks, is to end with a slide that shows some of the biggest names, scientists that we know, such as Oppenheimer or Spitzer, and those are people who are really nuclear astrophysicists, even though we know Lisa Meitner, so we know their names as people who made very led very important projects or made very important advancements in nuclear physics. But really, their original motivation was to study how elements are produced in space. So astrophysics and nuclear physics go hand in hand, and fusion should not be thought of this exotic man-made process that's super expensive and difficult that we're trying to make. It should be thought of, this is the preferred way in which the universe produces energy. So to a student, even at elementary school, I would like to say, the sun, right? You've heard about the sun. You already know about plasma and fusion.
Exactly. Cool. Yeah. And we can definitely be
Very
in touch.
cool. Thank you.
Yeah, you can contact us later on for details.
Absolutely. Thank you so much. And I apologize for not having my camera on. Those kids wore me out today, but you guys all did amazing. So thank you.
Yeah. I can also read out what Yashika wrote in response. Is that one misconception is that have realized around fusion is the nuclear fusion can be dangerous and it can be weaponized. That is not true. It cannot be weaponized, because all the fusion conditions are extremely hard to achieve, right? Reducing its possibility of fusion reactions being used as a weapon. So it's very different from, when we think of nuclear reactors and nuclear, missiles and stuff like that. Fusion is very different from that. So thanks, Yashiga, for pointing that out.
Thank you.
Yeah. Yeah, I mean, we can hang out for like 10 more minutes if people have questions or anything. But yeah.
I wanted to just pop in and say thank you, Mommy. Appreciate that question. But also thank you everyone for logging on. Unfortunately, I have to go return the rental car. So if you have any questions for me, I will pop my email in the chat, or you can just stalk me. That's cool too. But I am always happy to yap about science, and I love fusion. So thank you, everybody, and take care. Have a great day.
Cool.
Hello.
Hi, Akhil. Yeah.
Hi, yeah. So I'm a master's student and I was planning on, or I applied for a PhD program in superconductivity for fusion applications this year. But unfortunately, I didn't get into the programs that I wanted. And so my question is like, for future applications, what sort of experience do you guys recommend that, people who want to apply for a PhD in this field or in plasma materials, like what sort of experience should we get in the meantime?
Right. So I might, I can again open it up later on to other professors. And I can say that how we look for students, when we look for students, what kind of things we see. I think when we start our PhDs, me included for my own PhD and all of our students, we have something in mind, but our PhD takes us to wherever it takes us in that sense. So it's very hard to get very narrowed down in getting a, like, if you say you want a PhD on plasma material interaction, I think that is broad enough that you will have many options to choose from. Apply to, multiple universities with the same field of research, but the what your topic and degree would be exactly, the title of your thesis. It's kind of exploratory. Research is exploratory. We find things, we start doing research with one thing in mind, we find newer things, and that's research. We solve bigger challenges. So don't feel bad about, that you did not get into exactly the group that you wanted to, because life will bring you back to it. When you do your PhD, with your experience, it opens up way more connections and way more options for you. And so plasma material interactions have, as I say, as we talked about it, that it is extremely important. And so not just superconductivity, because it makes it more narrow to build the magnets, but I think you will get into a group if you just, again, patience and stick to it and don't lose hope. And email us if necessary. Exactly. Oh, thank you, Eva. We organize a graduate school and careers day every year from APS DPP, where Eva is also one of the XCOM members. I'm also on the outreach team. Eva, if you want to give a spiel on the graduate student day, please.
Yeah, so I would say this is because obviously fusion is changing, like this field is very dynamics. We tend to recommend treat fusion and plasma physics together, right? And you can think about it. Those topics live both in physics departments and engineering departments in the different schools. So because of this kind of a unique interdisciplinary feature, there are many programs that may be buried that you just haven't heard about because they don't have like a big a nuclear materials program or department, but there may be faculty who does this. So one thing we've been doing is, so I shared the link to last year's graduate school and careers fair event. And it consists of, on this link, on this page, you can find links to talks about how to apply to graduate school, just in general. What is a good application timeline, practices, how to apply for other jobs beyond graduate school, because maybe if you have a gap year or you couldn't get in this 1 year, you can still get engaged in a job related to your field, and that actually will boost your application next time. Then it also has the spreadsheet of programs in the US. This is a very valuable resource that we know of, have plasma and fusion faculty. And we also list, okay, what is the school? Where is it located? Who are the faculty contacts? We try to update it every year. And what are the topics? And I would say this is a gigantic list, but you can go through and you can look for, okay, who is more materials, but also, maybe think broadly. Because if you want to be in fusion, you can start with a more general plasma program and then work your way into plasma material interactions and a nuclear fusion type of PhD. And we also have this panel that I believe is recorded. There's a video of this where the people talk about different undergraduate and graduate fellowship and scholarship opportunities. So I think hopefully I'm going to stop here. Hopefully this provides resources that can help you, but also feel free to follow up with us if you have questions related to a particular program or a particular resource. We tend to sort of know most people in the field, in the US, for sure.
Also, I just want to add from the student side, I actually just went through this application process in the last 2 years, and I will say the admission cycle for the last 2 years have been really difficult, so please don't be discouraged. I don't think I really got anywhere my first round, and then because I was a master's student, or still am, and then I ended up doing research before I applied this past round, and now I've gotten to a PhD program, but I only got into one or two out of 10 that I applied to. So please don't be discouraged. Definitely apply again. If you can get some research experience, that seemed to help me a lot. But definitely it's been rough. So, oh, and the feedback I got from places I applied was also making sure to verify the people you're interested in working with have funding. With everything up in the air right now, reaching out and making that connection beforehand and making sure they have funding goes a long way. Because sometimes the issue, at least last year, was that they wanted to work with me, but they didn't have the funding to accept any students. And that kind of happened again this year as well for a couple of schools. So just hang in there. You got it.
Yeah, and then same, just tagging on to that is that, if you when you write the essays for graduate school, if you can kind of find commonalities, the skills and experiences you have, and the skills and experiences that the group needs and looking for, if that match, that's even better, then, and so having some research experience in summer internships, anywhere, any kind of research experience, theoretical, computational, experimental, hands-on research, anything helps. That's true. That's very true. Good.
Okay, thank you very much.
Yeah, okay. Yeah. Yeah. So if there are no more questions, we can drop off. If there are questions, we can chug along for a little bit. I do have to go out. I mean, I have an undergraduate student interested who wants to see our lab, so I should go out and bring him in. That's how we get to know each other, right? And or hey, Laura.
Thank you all.
Yeah, Laura, if you have all the questions that you have, you can ask us tomorrow and the rest of the week. And thank you, Daniel. Thank you. No, this was very nice. And thanks for joining. It's important. Important that you join. Cool.